In this next example of an application of differential equations, we are looking at a model of population. So the population of a certain tropical island is currently 800 people, and in the absence of immigration or emigration, it increases at a rate proportional to the population itself. So a few, again, keywords. So once again, we see that the description of a rate, hinting that we are dealing with a differential equation. We also have this proportional to phrase. And the other thing I'll point out is the idea that we're talking about an increase here. So, of course, we're not done reading the question, but I want to point out again, what I would start with is identifying some variables. So I'm going to let's choose this. Let y of t equal the population on this island after t years. And this one really tells us years as the unit in those parentheses there. So I can start off, first of all, dealing with the proportional to, but I want to point out there's more information in this expression. So, however, each year 35 people immigrate to the mainland, and we want to find and solve this. I guess they're giving us a variable, so we'll call that n of t. So we want to solve for this population n of t. So a couple of things to consider here. What we didn't have to involve in our previous example is that in general, there's two things going on here. So when I'm expressing my derivative here, I'm going to express it as the rate in minus the rate out. So that's the way I want to think about that. There's two things acting on the population here. In one sense, it's growing, and it's growing at a rate proportional to the current population, but it's also declining because a certain number of people are leaving every year. So in order to accommodate both of those things concurrently, I can include them in the expression. And of course, the negative sign is reflecting that idea of a decrease, and the positive rate n is reflecting the increase. So in a problem like this, I really want to view those two things separately so that I can then combine them. So in this instance, the rate in is the first thing that's being described. We're told that it is increasing, the rate there is increasing at a rate proportional to the population itself. So the population itself is exactly what n represents. And in this case, they're giving us the proportionality constant. And I can put it in as a positive constant because I know that we're dealing with an increase. If they had that first sentence exactly the same, but the word increases was replaced with decreases, I would have to supply the minus sign there from that information. So this rate in is very much like our previous example, so I can really build off of what we saw there. However, there's a rate out, and the rate out is saying every time unit of 1 year, 35 people leave, and so that rate out is going to be constant. A common question I get asked here is, why is it not 35t? I'll point out that if that's what you're thinking of how that might affect the n of t, right? But if we're talking about this constant number of people leaving each year, the way that affects the rate of change or the derivative is that the derivative there would be a constant. So we're having this every increase of the time unit by, say, 1 year, we expect 35 people to leave. So we think of that as a constant. Now, putting these two bullet points together with my general expression above, this tells me then that dn dt is the rate in minus the rate out. So this is the equation we want to solve. Now, this is separable. Don't be thrown by the minus sign. And the reason it's separable is that the entire right-hand side is a function of n. So I could view that as that times 1. So thinking of like the function of t being 1 here. So when I separate these variables, importantly, I have to take the entire expression, because remember, we're not separating it by a minus sign. We're thinking of a product. And we're setting that equal to 1 dt. Now, if I take the antiderivative of the left-hand side, we have to be careful with this constant multiplier. You could do a u substitution, or if you just want to kind of reason it out, keep in mind that we do get the natural log of the absolute value of that denominator because that is a linear expression involving the integration variable. But I have to put 1 over 0.03 out front to counteract the chain rule that we would get if I were to differentiate this log expression. That would come out directly if you did a u substitution. We're setting this equal to the antiderivative of 1 with respect to t. So that's going to give me t, and I'm going to put my integration constant on the right-hand side. I want to solve for n, which we see is in here. So we've got a little bit of work to do. I'm going to multiply both sides by 0.03. And what that will do to the right-hand side is I can write that as 0.03t. I'm going to write it as plus c because I absorbed the constant multiplier of 0.03. But it is also fine if you were to write here plus 0.03c. We should end up at the same final answer. Now I'm going to raise e to both sides. That gets rid of the log expression on the left-hand side. And on the right-hand side, I could write e to the 0.03t plus c. Or, as we've seen, I could write that as c times e to the 0.03t. Again, that's using my properties of exponential functions. Now, I want to add 35 to both sides. And we get 0.03n is this exponential function plus 35. And then finally, I can divide both sides by 0.03. And we're going to get that n of t is ce to the 0.03t plus 35 over 0.03. Again, it would be fine if you had written the first part divided by 0.03. I'm just treating c over 0.03 as my constant. All of these things are fine. And in fact, I will say an easier way to write this fraction that I've introduced here on the right-hand side, because I'm dividing by a decimal, is if I multiplied the top and the bottom by 100, this would be 3,500 over 3, just a little bit cleaner since I'm doing this by hand. Now, that's our solution function. We haven't used all of the information yet. We are given that at time 0, there are 800 people on the island. So y of 0 should be 800. If we plug in 0 to our general function above, we get c plus 3,500 divided by 3. We want that to equal 800. So we see that our c value is 800 over 3, so 2,400 over 3, minus 3,500 over 3. And this is negative 1,100 over 3. That's our c value. So n of t is equal to, negative 1,100 over 3 e to the 0.03t plus 3,500 over 3. Now, one of the things we were asked to do here, which required us to actually come up with a solution, is we want to find the time when the population becomes 0. Notice that we would be able to do that here because I have the function of the population as a function of time. So we would want to solve 0, set 0 equal to n of t, and solve for t. So again, this just becomes an algebraic manipulation, or arithmetic really in some sense. So I can multiply both sides by 3, and we would be able to then say, subtracting this over 1,100 is equal, 1,100 e to the 0.03t is equal to 3,500. If I divide both sides by 1,100, we get e to the 0.03t is 3,500 over 1,100, or 35 over 11. If we take the log of both sides, 0.03t is now the natural log of 35 over 11. And if I divide both sides by 0.03, we get t equals 1 over 0.03, natural log of 35 over 11. And of course, that's not a terribly nice way to look at that. If I were to evaluate this on a calculator or computer, we find that this is roughly 35.58 years. Okay, so that answers the second part of the equation or example. And so kind of looking at the process, it was important that we first set up an appropriate differential equation, which we could then solve. And then we were able to use that solution to answer further questions about the example.